Hello everyone, trig equations or trig identities part 2 here. We're going to look at a few more things that are crucial with trig identities. So let's explore this one topic, non-permissible values. So it says use the quotient identity to show that sine x equals tan x over cos x. So tan x we know is equal to sine x over cos x. Okay, and if we multiply that by cos x, really cos x over 1 if you're multiplying by a fraction. So let's change that to over 1. You'll notice that these common factors of cos x, one on the top, one on the bottom, can cancel, and you're just left with sine x. Okay, so we've shown that the right-hand side can equal the left-hand side. Okay, part B says, is this statement true for all values of x? Well, let's take a look at that. We're going to investigate that with a couple of graphs. So let's bring up our calculators and we're going to graph in y1 sine x and in y2 tan x cos x. Now above we've just kind of shown they're equal, so let's see what that looks like on a graph if they're equal. Set your window settings 0 to 2 pi and negative 1.5 to 1.5 for y. Okay, so go ahead and pause your video and let's do that. Okay, so did you get sine x in y1, tan x cos x in y2? We set our window settings to what they said. And then it was funny because before I changed the mode, my graph looked very weird. So check your mode too. You should be in radian mode, otherwise your graph could be looking very straight line-ish. Okay, so radian mode, and then let's take a look. Okay, now I'm pretty sure we graphed two functions. Where's the other one? Well, two ways you can check that out. One, if you hit trace, see how this equation came up in the top left-hand corner of your screen? If you hit the up or the down arrow, you'll notice we moved to a different graph, it says, but our cursor didn't move. So it appears that the second graph is on top of the first one, but how can we check that for sure? Let's change this second graph. Go over to these lines on the left-hand side. That changes the line type. So if we change that, hit it once, now it's a bold line type. What we can do is we can see that one plot over top of the other one. So let me show you what I mean. Let's hit graph. Okay, so see how that second one plotted on top of the other one perfectly? Okay, there you go. So let's see if we can graph that one back to our, so it looks like pi, it's kind of crossing. Okay, so let's draw that here. Hopefully a better line than I just did. That's funny. Okay. Try it from this way. Maybe it'll be easier. Nope. I'm just like Aunt who drank too much Kool-Aid. Okay. So drawing this stylus. Okay. All right. It appears the graphs are identical and that f of x equals g of x for all values of x in the interval. However, it's not actually true. So let's evaluate what f at 2 is. So f of x, just to write this down again, was equal to sine x, and g of x was equal to tan x cos x. Okay, so let's figure out f at 2. So f at pi over 2, we sub pi over 2 in for sine. Now, whether you do this on the unit circle or the calculator, it doesn't really matter, but if you want to bring up the calculator, we're in radian mode, so that's good. Let's quit out of our graph and go sine of pi divided by 2. And those of you on the unit circle, hey, it's 1. We already got that 10 minutes ago. Okay, so equals 1. G at pi over 2 equals tan pi over 2 cos pi over 2, and let's bring up the calculator again, and we would go tan pi divided by 2 cos pi divided by 2. Okay, let's take a look. Error. Okay, so if you hit enter, or go to, I should say, it takes you to the spot where it's having the issue. And apparently, right after it did tan of pi over 2, it had a nervous breakdown. Okay, so undefined there. Okay, now if you think about that, up here at pi over 2, coordinates 0, 1, tan is y over x, so we would be going 1 over 0, and you can't divide by 0. So this one in particular is undefined. All right, now let's try this again. Actually, you guys go ahead and try f at 3 pi over 2 and g at 3 pi over 2 and see what you get. Okay, pause your video. Okay, so you probably got -1 for f of x, and again, it turned out to be undefined for g at 3 pi over 2. So f at 3 pi over 2 was -1, g at 3 pi over 2 undefined. So what do you notice? The conclusion you should draw from this is that actually it looked like from the graph that they were equal, but actually f of x does not equal g of x at x equals pi over 2 and 3 pi over 2. So these points of discontinuity that the g of x function has, okay, it says explain why using the results in A. I would just say that tan x, or tan at pi over 2 and tan at 3 pi over 2 is undefined. Okay, meaning you're dividing by 0 there. Okay, show the correct graph. Okay, so the correct graph for tan cos x, it'll look mostly the same, except at pi over 2, it would be undefined. So it looked before like it was up here. So what we're going to do is do a little dot there and do a little dot down here because that looks like where it was. And then the rest of the graph would look the same. It's just we've got holes in the graph happening at pi over 2 and 3 pi over 2. Those are called points of discontinuity. Oh yeah, we did those in rational functions. You know that. Okay, so in 20-1. All right, we say that sine x equals tan x cos x is an identity, but with non-permissible values, where cos x, because it's tan x over cos x, oh, that was nice. That's a snowplow going by, if you heard that. Alrighty, tan x over cos x, so that means the denominator, cos x, can't equal 0. Just like before with rational expressions, can't divide by 0, so you take a look at what's being divided by 0. Tan x over cos x, there we go, cos x can't equal 0. We're going to do more of that. So then the restrictions on the identity, generally speaking, and this is how you usually write restrictions, is that x can't equal pi over 2. You go to your first one, okay, and then how far apart is the next one? Well, they're pi apart, so that would be your restriction. Kind of like writing a general solution. All right, so they're talking about zoom trig and how you might be able to see it in degree mode. For sure, not in radian mode. I wouldn't even bother trying to see them. You just have to do this algebraically, okay? Let's take a look at the next page. Okay, so when you're trying to find non-permissible values, two things you should focus on, okay? There's the obvious one, this one, is if it has a denominator, then you set that denominator to 0. Set to 0 and solve like it's a general solution. Okay, with the NPI stuff. Okay, the other one, I call these the sneaky identity, or the sneaky restrictions. Sneaky NPVs, okay? Those are the ones that don't appear to be dividing by 0, but because they are actual ratios, like tan x is sine x over cos x, we just saw that in the first example, cos x can't equal 0, right? And secant, again, 1 over cos x, where cos x can't equal 0. Okay, so non-permissible values where cos is 0. Cotan, cos over sine, and cosecant, 1 over sine. So that's, you'd be looking at where sine x is equal to 0 to find your non-permissible values. Okay, the non-permissible values are also called restrictions. All right, they're just talking about general ways to write that, but we can do that later. Okay, hints in proving identities. I actually have some strategies for proving identities that I've printed up and that is available on D2L. But you can also, I think I've handed a copy out in class. So let's take a look at that right now, please. Okay, so if you're trying to prove a trig identity, which basically means letting the left, or checking to see if the left side equals the right side, but not subbing in a variable or a value for the angle, I mean. You begin with your more difficult looking side. It's a lot easier to make something difficult look simple rather than the other way around. So here's what I've developed. 3 steps, okay? You may or may not begin on step 1. It depends if you can do anything on step 1. And then you might go to step 2. You might be able to do it. And if not, step 3, again, you may do this, you might not. So it's sort of like you don't have to do every step. It's sort of like if you can, you do. So first step should be to simplify. Now that could mean either expanding stuff out, multiplying. It might be the opposite of that, which is factor. You usually do that when you have something like sine to the fourth minus cos to the fourth, or if you have a greatest common factor, you can factor out. Okay, all 3 of these are referring to fractions. Okay, so if you have, or rational expressions really, if you have a denominator numerator, you might multiply denominator and numerator by the conjugate. When do you do that? It's when you have 1 plus sine theta, 1 minus sine theta, 1 plus cos, or 1 minus cos. Okay, and really those are the only kinds. I put etc., but you can get rid of that. Add, subtract rational expressions, get common denominator. So if you have 2 fractions and you're adding or subtracting them, you would want to get a common denominator, okay? Or finally split into 2 rational expressions, doing the opposite of common denominator, by dividing the terms in the numerator by the denominator. This strategy only works if you have 1 term in the denominator. Okay, step 2. And this one you should always keep your eyes open, regardless. Look for squared identities. So, you know your Pythagorean identities? Okay, always keep an eye open for any of those. Sine squared, cos squared, tan squared, secant squared, etc. Okay, and then finally step 3, convert to sine and cos. You may or may not do this step. It might actually be sometimes the first step you do, but it should always be the last resort. Assuming you've tried everything else, you're going to do that as a last resort. Okay, and let's say you get to step 3, you might recycle back around to step 1. Okay, let's go back to our notes and try some examples. Okay, in this first example, we're doing several things because there's different parts. First, we're going to verify, which simply means to sub this value in for x to see if the left-hand side equals the right-hand side. So that doesn't really show that the identity is actually true. It just shows it's true for that particular value of x. So we'll start with that. Okay, so on the left-hand side, we'll have 1 over cos, and we're subbing in pi over 3. And then we have minus cos pi over 3. Okay, on the right hand side we have sine pi over 3 and tan pi over 3. Okay, so let's grab our unit circle. You could also use the calculator for this. It depends if they want the final answer as an exact value or not. Okay, so here's pi over 3 on the calculator. The coordinates would be little x, 1/2, big Y, root 3 over 2. So we want, first of all, 1 over the cos, which would be the x-coordinate. So that would be 1 over 1/2, minus, again, the cos values, so 1/2. All right, 1 divided by 1/2, dividing by a fraction, multiplied by the reciprocal, that will become 2. 1 divided by 1/2, I'll show you that off to the side. There we go, that equals 2. And we have 2 minus 1/2. Okay, common denominator, put that over 1, we'd have 4 over 2 minus 1 over 2. There we go, 3 over 2. Okay, if you did it all in the calculator, you would have gotten 1.5, which is fine. Okay, sine of pi over 3. So sine is the y-coordinate there, so root 3 over 2. So we're working on the right-hand side now. We need to show that they're equal. Tan, well, tan is the y over the x, so root 3 over 2 over 1/2. And as you know, when they're both over top of 2, they can cancel off. Our work with the unit circle, we did that quite often. Okay, so now we have root 3 over 2 times root 3 over 1, if you like, really. Okay, so multiply your numerators. Root 3 times root 3 would be 3, or root 9. And 2 times 1, 2. And there we go. Left side equals right side. It is verified for that value, verified for pi over 3. All right, we can also verify with the graphing calculator to show that it's probably an identity. Okay, and if you recall from our first thing, when they graphed on top of each other, we showed that it was. Okay, so you guys go ahead and put that in, check that out, it should work, and then I'll see you in the next video for the proof part. All right, thanks for listening.